Alrighty, so we're going to put this on page 60. So as I said, we're rewinding back to 6.1. And when we were doing the approximations, because we have now actually taken the integral of some things and looked at that a little bit where we can do it a little bit more exact. We haven't gotten to all the properties and stuff yet. But we've looked at the fundamental theorem of calculus at least, see how that relates. But another way to approximate is with trapezoids. Now, Riemann still means rectangle, so these are not Riemann sums, but they are sums, and they are trapezoidal approximations. And if you look, and I know we talked about trapezoids like a tiny bit because they were drawn on something we did on that first set, but if you look at these, how we're trying to estimate the area under the curves here, and instead of making left or right rectangles, we're making trapezoids, which seem to be a little bit more accurate really than either one of the rectangles. Would you agree with that? Okay. And so again, just another way to do it. So another shape, they're easy to find the area of. Now, here's one form of the formula for the area of a trapezoid. Something that you do have to know, okay? So I will show you a couple of other things, or I'll show you how I usually in geometry would teach. This is how you can just know what it is. Because I'm quite confident that if I gave you a triangle and I asked you for the area formula, what is the area formula for a triangle? 1/2 base times height, or base times height over 2, but sometimes this one's better, especially if you've got fractions in it. All right, so then if we take a triangle, whatever kind of triangle it is, and we chop its head off parallel to the base, then that's going to create a trapezoid of some sort, right? And then instead of having one base like a triangle does, we now have two bases, base 1 and base 2, right? And then so the area formula of a trapezoid, if you know this formula, it's pretty much the same except we have two bases now, so I can do 1/2. Instead of base, it's base 1 plus base 2 times the height. Okay? 1/2 base 1 times base 2, or 1/2 times base 1 plus base 2 times the height. So see how these are very, very similar? And if you have two bases, you just add them together instead of putting the b there. Or you can use that formula there if that makes you happy. Or you could also use area equals the average of the bases times the height. Whatever works for you, however you can remember it. Okay? I think I'm going to stick with this one myself. Would you agree with that? Just kind of relates to the triangle, probably makes the most sense, of not like a brand new thing you have to know. All right, so, and you understand what the area under the curve looks like. So we're going to do these questions. Also, I don't know if you recall, but on one of the Riemann sum ones we did early on, it said like use 3 subintervals, but it didn't break up into 3 easily, and we kind of had to combine something. And I was thinking as I was doing it, this is weird. I don't think this will actually come up. And I was right. There was a mistake on there. So you won't have to overthink something like that. Just going to throw that out there. So here is what we have. An amusement park opens its doors at 9 a.m., t equals 0. The rate that people enter the park at time t is modeled by the function p prime of t. You see it is a rate, and notice your units are in rates. It's a rate type unit. Modeled by the function p prime of t and thousands of people per hour. You also want to pay attention to something like this when you're writing your units out. So we make sure that we write it out correctly and don't just put however many people. It's thousands of people. Selected values are given in the table above. So it says use trapezoidal approximations. We don't have to draw a picture, okay, because we can do it from the chart. And it says with 3 subintervals indicated in the table to estimate the total number of people. So if I start trying to break up my intervals here, this is 1, 2, 3. Well, I actually have 4 of them, right? So maybe I don't start at 0. But it does say t equals 0. We go from 9 a.m. Well, 9 a.m. to 7 p.m. is how many hours? 10. So what I really am wanting to do is go from t equals 0 to t equals 10 hours. So I'm not going to use that last little group of stuff there. So pay attention to what you're actually using. All right? So remember the change in x, that is your base of, or actually it's a base of one of your rectangles. This is actually the height of your trapezoid. Because the trapezoids are standing up, they're drawn sideways. So that is your height. These two are your bases. Okay? So height here, when I just find my change in x, this is 2. Sorry. Okay. So this is 2. The difference here is 3. The difference here is 5. Do you agree with that? Then what I suggest you do, because it is so easy to use the wrong numbers off the chart, is that when I'm going this, I need the change, and I need my dt, the change in the time. I'm not going to actually use the time. I use these numbers to get these. So now I'm going to mark them out so I don't use the wrong thing. If it was a left-hand rectangle, I would use this as the base and this as the height. If it was a right hand, this would be my base, this would be the height. But it's a trapezoid, so I have 2 bases, so I'm actually using both of them each time. Okay? So it says total number of people. So if I integrate p prime, I'm going to get p, so I can say p of t, which would be the total number of people, which would actually be p of 10, is what I want, because it's 10 hours, right? Is approximately, squiggly equal signs, right? Then I'm going to open my brackets. My trapezoid formula is 1/2 times. These are the 2 bases that go with 2. So 7 plus 11 times the height, which is 2. Plus 1/2. I go on to the next one. My 2 bases are 11 and 8. 11 plus 8 times the height, which is what? 3. Plus 1/2. Then I'm on to the last one. 8 plus 4 times 5. Okay. And I put all that in brackets because I want to be able to put my units on there. What are my units? Thousands of people. I don't even know what the actual number is, and I know it's bigger than this, but 3 people wouldn't make sense, right? But 3,000 people would make sense, yes? So make sure you're paying attention to that here, and it's here. I mean, it's written 2 different times for you, so make sure you don't miss that, because that could be a point, and honestly, that's a pretty easy point. And even if you miss the other points, maybe you get the units point, right? Everybody okay with that? What questions you got? Okay. So in this previous example, we approximated the value of this. We wrote it as p of 10, but we were integrating from 0 to 10, right, of p prime. In context, we were approximating the total number of people that entered the park from 9 a.m. to 7 p.m. In general, we need to carefully consider whether we have found the total or the net change when interpreting a definite integral. Okay, and so here's the difference here. You have the total if you were only adding parentheses or subtracting areas. So that means, like, in the sense of these people here, we were only adding people because we didn't care about there was 0 people there. We were adding them. No, we didn't say anybody was leaving the park. Or we could have said at the end, nobody else is let in, and we're just going to start letting people out, and this is the rate at which they're leaving. So it could be all adding or all subtracting if people are coming or going. Your net change, and what happened, is when you were adding and subtracting. Areas. So if we said this is the rate that people are coming in, this is the rate that people are going out, and then we could figure out the net change, not how many people entered or how many people exited, but we're doing both at the same time or something like that. Okay? We're not going to focus on this too much at this point, but I just wanted to at least throw it out there, and we're going to start kind of thinking about things a little bit like that. Everybody okay so far? All right, flip it over. So the amount of money in a bank account is changing at a rate of A prime of t, where A is measured in dollars per day, and T is the number of days since January 1st. Interpret the following in context. Okay, so remember, this is estimating an area under the curve, and it's negative. Can we have a negative area under the curve? Yes, because that's when it would be below, right? Or maybe we had above and below and there was more below, right? So you're adding and subtracting. So if we're talking about a bank account, we can put money in and we can take money out. Yes? Bless you. So if I can put money in and I can take money out, is that going to be a total or a net change? Am I adding and subtracting? Yeah, it's going to be a net change. Okay, so the way we want to write this, make sure I get my words right. Okay. This is the net change in the amount of money in the bank account, or in a bank account, I guess. From T equals 0 to T equals 10 days. It's not necessarily the total, or it's not necessarily the total amount of money in the bank account. I mean, even if it was a positive number, that's still not necessarily the total amount because we don't know what we started with. We don't know what the account balance was on January 1st. So just because it looks like this doesn't mean that the account balance is negative, right? Maybe we haven't gotten paid yet, but we're just spending money and there's still money in there. So that's the net change, okay? But it's the net is still kind of means total. It's the total change. It's not the total amount that's in there. Those are what are different. Okay, you okay with that? All right, so then the next one, the rate in dollars per day that Mr. Passwater spends money can be modeled by this function, where S of T is modeled by this function S of T, where T is the number of days since January 1st. Interpret the following in context. Okay, if we're just looking at what he's spending, are we adding and subtracting? No, we're technically just either subtracting or adding, however you want to look at it, but it's just one or the other. So it's not the net change, it is the total. This is the total amount of money Mr. P, he has a long name, Mr. P spent from T equals 0 to T equals 10 days. Notice on both of them, they're both money, right? So both the rate of the money times time gives me money. So we're both talking about money. We could even be talking about spending money in both of them. But the way that things are worded, you have the total change or the total amount, okay? And we'll work through more of those where we can see the differences. Okay, what questions you got? Okay, so this chart looks very overwhelming, but it'll be fine, and you can draw yourself little pictures to remind yourself of things. Did I say something wrong? Well, the rate can be changing. The keyword, and this, the way this is worded does bother me a little bit because I kept saying, well, we don't know if money was added and subtracted. Maybe money was only subtracted. But the only way we would know that is that if we knew that the bank account was 0 on January 1st. Because even if only money was subtracted, there was already money there. Does that make sense? And you had the possibility of depositing and withdrawing money. When you're talking about spending money, you're only going in one direction. Okay? That help? That's a good question. Yeah, or like if he spent money but then got some refunds or something, you know, then that would be the net change and not necessarily how much he just put out into the world. Does that make sense? That's a very good question. Anything else? Okay. And those will get better with some more like real examples once we start doing that, I think, but those are very, very good questions. Okay. So in calculus and the real world, because the real world is full of calculus, even though you don't recognize it quite yet. Not that you have to do calculus every day. I don't mean it like that. We often need to make approximations or estimates, right? We can approximate a value in general. It is generally because we are not able to find the exact one. Even with knowing that, it is important to know if your estimate is an overestimate or an underestimate, okay? And so, like if you're at the store and you're trying to figure out if you have enough money to pay for stuff, it's kind of probably better to overestimate how much you're spending so you don't get up to the cash register and embarrass yourself, right? So sometimes it's a little better to kind of overestimate, especially if you're just kind of ballparking the figures in your head. You don't want to get up there and be counting your pennies and not have enough. So it's important to know which direction we're going. Okay, so like I said, this chart looks very overwhelming. I mean, again, I understand this stuff and it looks overwhelming to me. I want to first make sure you understand what f of x is here. Let's say we're going to take the integral from a to b of f of x dx. So it's what we're taking the integral of, not our answer. Okay. So a lot of times this would actually be f prime, or it could really be anything, but it's what we're taking the integral of. So if we have if we talk about our Riemann sums with our rectangles, we have left and right hand rectangles, right? And they are either overestimates or underestimates. We did look at that on the first page, but it depends on what's happening with the function. If the function is increasing, one thing happens. If it's decreasing, another thing happens. And again, you can draw yourself little pictures. Let's just say that we have this function here. And let's say that our function is increasing the whole time. Then if I'm going to do a left-hand rectangle, that means I would drop this down. I have two things, A and B, right here. And then, but I start from the left and draw it so I can see that when it's increasing, if I keep drawing my rectangles, that's totally going to be an underestimate, right? And I don't have to draw the whole thing out, but I can kind of sketch a couple things like that to make sure I wrap my mind around it correctly. You with me on that? And so then once you've got one of them, okay, if I'm doing a left hand and it's increasing, it's an underestimate, which means this has to be an overestimate, and then the right hands are the other way around. So you really only have to do one to make sure you get everything all lined out correctly, okay? So left hand, if it's increasing, it's an underestimate. I just proved that right there, just by my little picture of 1 or 2 is enough. That means that when if it was decreasing, and if you need to draw yourself those two, we can. So let's just do that. So if it's decreasing, then when I do a left-hand rectangle, you can see that it's an overestimate. And then the right-hand rectangles are just the opposite of that. And then you got all 4 things down, okay? So when you explain yourself, because you might have, you can't just draw yourself a picture and say it has to be increasing. But if it's over or under, you have to say because whatever this is, which is f of x in this case, is increasing or decreasing. And that explains how you know if it's an overestimate or underestimate. We may or may not be finding a sum to actually talk about that. Maybe it's just a random question that asks you if it's an overestimate or underestimate or whatever. Now, the midpoint and the trapezoids get a little weirder here, but here is what's happening and what's really going to help you figure this stuff out. And there's not a whole lot of, how's your paper? Where do you have some room down here? Okay. You have a little bit of room right here. We're going to write out our fun chart. See if you can write your fun chart without looking at mine. Because it's been a minute since we talked about it. That's basically what it should look like, right? Because once we start talking about f double prime, we're integrating f. We have to know something about f double prime. We're not actually going to take the derivatives to figure that out. But I will know some stuff if, in fact, f is increasing or decreasing. We can figure that out. We know if f prime is positive or negative. And then if we can see a graph, if I actually graph it like this, I know that both of these that I happen to draw, they're both concave up, right? If they are both concave, if they're concave up, then your second derivative is positive, okay? So if the second derivative is positive, you have an underestimate for midpoint, overestimate if it's less than 0, and then for trapezoids, it's opposite again. And when you're thinking about these, make sure you look at concavity. And again, let's draw ourselves a trapezoid. I think that those are a little bit easier than the rest. And I will just draw a picture just like I had before, like this. If I'm going to draw a trapezoid, we go from here to here, and I connect those, you can literally see, with that being concave up, Is that an overestimate or an underestimate? Over. So for the trapezoids, if we're concave up, and when we're concave up, it's positive. So when it's positive here, it's an overestimate. Okay, so this is up, down, down, up. Okay, and talking about concavity there. It's one way to kind of remember that. Everybody okay with that? Okay. Alrighty. So, with all that said, is that the other side of your paper? Okay, I have another sheet for you. Never fear, we're not done. I know, it's terrible, right? Okay. Thought you were free. So this is still going on page 60. You can put them on the same page. Okay. We have the graph of f, right? And it tells us the function f is twice differentiable. Then it gives us this information. It does not have to give me that information because it gave me a graph. Write out your fun chart again. Oh, and don't huff at me. By looking at this graph that they gave me, is the graph concave up or concave down? Concave up. It is concave up, therefore f double prime is positive, which they told me, but again, they didn't have to. Is this function increasing or decreasing? It is decreasing, which means f prime is negative, which they told me, but they didn't have to. Okay? So if they don't tell you, you do actually know it from this. All right? Does that make sense to you? We good on that? Okay. And it may actually say things like it's concave down or it's decreasing or whatever, and so that you have to be able to kind of put all those pieces together. All right, so LS, RS, T sub S, they represent left Riemann sums, right Riemann sums, trapezoidal sums. Okay, makes sense? Left, right, trapezoids. And then this is the integral, which would give us the exact answer. So what we want to think about here is one of these two is an overestimate or an underestimate. And now, when we look at this, it says, which of one of these are true? Now, you can sit here and play with it and overthink it, but I think just thinking of it globally before you ever try and reason through any of these, because I think you'll get halfway through and your brain will hurt, and then you're going to be really confused about anything that's going on. The first thing is, I'm going to take my integral from 2 to 7 of f of x dx, and since I have, and I'm just going to look at the left and right rectangles first. One of them is an overestimate and one of them is an underestimate. And so one goes on either side of that. Would you agree with that? Whatever the actual sum is, then one's bigger and one's smaller. So since this is decreasing, and if you're not sure, you can draw yourself a picture. Okay? Which one is the overestimate here? Is it the left or the right? The left. Would you agree with that? Because if I draw that rectangle in here, I drop a line here. Ooh, that is not straight at all. I drop a line down here, and let's say I go to here, whatever. And then that means I'm going to go from the left, and I can see that my left hand is the overestimate. You agree with that? So since it's the overestimate, it goes here. The left-hand sum, which means this has to be the right-hand sum. So I know for sure that the left-hand sum is greater than the right-hand sum. Would you agree with that? So let's go through here. Can I mark out A? Is the left hand greater than the right hand here? No. So A can't be it. We haven't talked about trapezoids yet, but that's okay. Here I have left hand greater than right hand greater than right hand isn't even there. So, but at least now, if that's all you can figure out, now you're guessing between 3 instead of 4, right? I mean, worst case scenario, I don't want you to run around guessing. Hey, wake up, you're missing important, exciting things about trapezoids. Come on now. All right. So the next thing we want to look at is the trapezoids. So I'm going to take my integral again from 2 to 7 of f of x dx. Now, if you were actually doing this for yourself, you could maybe just draw an integral symbol, just because you're trying to figure things out. Now, trapezoid. I want to know if it's an overestimate or an underestimate for this. Now, I had that big old chart, but I also have a graph in front of me. And if I didn't, maybe I could sketch one if I knew what was going on. If I did this, I'll drop a line here, I'll drop a line here. When I connect the dots, is it an overestimate or an underestimate? It's an overestimate. So that means that f of x, this actual integral, is less than this. You agree with that? Now we have to figure out what's true about the left and right-hand rectangles. Well, let's think about what we did with the two sides. Didn't we just add them together and divide by 2? So basically it's the height of the left-hand rectangle and the height of the right-hand rectangle. If I look at, so if I'm going to use this trapezoid that I drew, if I use the same two sides and I did a left-hand rectangle, it would look like this. If I did the same two sides and I did this, I'd get a right-hand rectangle. So do you see how the trapezoid is really just the middle of the two, right? So it's the average of the two. That's why we're averaging the bases, right? So since it's the average of the two, when I line them up from least to greatest, I already know that the right is less than the left, and the trapezoid will always be in between the two. Like these two could switch places, but the trapezoids will always be in the middle. You with me on that? Do you understand why? Because we're averaging them, basically. Everybody with me so far? So these are kind of some things that, even if you don't remember it off the top of your head, you can write them down quickly. You don't necessarily have to use all the fancy notation. Like I said, you can just do an integral symbol. But now we have them in order for this, well, we don't have them exactly like this yet. But I have this. Is this true? No, because that kind of looks like this, but it's not in the same order, and we're pretty confident that's right. So now we get into this. I know that left is greater than right, but are they both less than the integral? No. So let's hope that this one's true, because it's the only one. Go ahead. The integral is the actual answer. It's we're estimating the integrals with these things. This is the actual answer. Yeah, the actual area right here. Yeah, this actual area, if I could find it, which I can't because I don't know what the area formula is. Well, we might be, yeah. So when it's like the trapezoid almost follows it, but this is actually follows it. And we're going to get into how we really find it. Yes. And of course, that also depends on the graph, and it also depends on but yes, in this case, it's just barely an over an estimate. Okay? Which makes it the best out of these three for this specific graph here. Okay? But it's also just an average of the pink and the orange, which is the left and the right. Okay? Good question. So now let's check this one. We hope it's right because it's the only one we got left, right? Is the trapezoidal sum greater than the integral itself? Yes, we said that right here, right? And is the left-hand side greater than the trapezoidal? Yes, because we said that right there. And that's your answer. Okay? Good. It's fine. Here's the good news. If that really makes your brain hurt, I mean, that might be one multiple choice question. It's not going to be on the free response. You're not, might be one, but I think you can figure it out if you don't stress yourself out about it. Okay? You can just draw a bunch of pictures. Just keep drawing pictures if you need to. That's why I'm showing you the different ways. That's fine. There's no shame in that. But the more we do it, the more it might make sense. All right, so let's look at this. Here we go. Y'all can do it. You can do it. All right, we got from 0 to 6 seconds, a large glass is being filled with water at the rate of W prime of t. They gave it to me. Measured in ounces per second, that's labeled for me. Selected values for the decreasing function, that's important, decreasing function, W prime of t, are given in the table above. Approximate this using left Riemann sum with 3 subintervals. Okay? So I can do 1, 2, 3. I'm going to find the change in t first. So 2 minus 1 is 1. 4 minus 2 is 2. 5 minus 4 is 1. Then I've used those. I'm going to mark them out so I don't accidentally use them. Okay? And then one of the things I think I did in that video is since it's the left Riemann sum, this is my interval. I'm using the left part of the interval for my height there. These are the numbers that I use, and I'm going to literally connect them together so as in hopes that I don't use the wrong number by accident. Okay? Because I'm going from the left side to the right, so that's the height of the rectangle that I'm using. So notation here is important also. The integral from 1 to 5, w prime of t dt. I'm approximating it, so it is approximately, I use my little squigglies. And Riemann, remember, means rectangle, so there's no question whether or not I'm using a trapezoid, right? It's going to be a rectangle, and it's going to be a left one. And I have 3 of them. So I'm going to do 1 times 2.3 plus 2 times 1.7 plus 1 times 1.2. What are my units? Ounces. Easy enough? We good on that? All right, so then it says, using correct units, interpret the meaning of this right here in the context of the problem. So if I had the actual number, like 5 or whatever it is, I have no idea and I don't care and I don't want you to figure it out. I want you to leave it like that. So you have just identified that this is approximately this right here. So you don't have to write out those numbers again. It has a name. We can say that the integral from 1 to 5 of w prime of t dt is, because that's what it's asking me to do. And is it the amount or is it the, what word am I leaving out? The approximate. Is the approximate amount, and abbreviations are okay. I would not just put APP, but APPROX, something like that's fine. Approximate amount of what? But ounces of what? Water. Or I could have put ounces of water, or that probably would have made more sense. Of water in ounces. And again, even though that might not, I mean, technically maybe we should have written out the word, but this is not English class, it's fine. It's the approximate amount of water in ounces that what? Read the question. That filled the glass, period. Are we done? Good. Glass from t equals what? 1. So look, from 0 to 6 seconds, it was when we're filling the glass, but they gave us from 1 to 5. That's what we were approximating, right? From t equals 1 to t equals 5 seconds. Notice, here's the difference with the whole net change thing. And I don't have to use the word net change necessarily. This is the net change. It's not the amount of water in the glass because it was filling from 0 to 6. This is only our snapshot from 1 to 5. So that's the amount that was added. That was the net change. It's not necessarily the total that's in there right now. You see the difference there? Okay. What questions you got? All right, so then I need an over or under approximation and give a reason for your answer. Now, we used a left-hand rectangle. If you're looking at the rectangles, left or right, do we care about concavity? No, we only care about increasing and decreasing, right? And what did it tell us? It was what? Decreasing. So if you're not sure, you go, all right, I have no idea what it looks like, and it doesn't have to be, just do something that's decreasing. And then go in there and do a left rectangle, and you can see that it is what? Over or under? Over, okay? So I can say answer in part A is an overestimate because W prime of t, okay, W prime of t is decreasing. That's why. What questions you got? Mm-hmm. Yes. Like this, yes. This is what a free response would look like, something like this. Yes, absolutely. And maybe even on the other side when you sit on the back. Yeah, I think I just spread it out more because I had some room. I think it's kind of the same. There's a little bonus question on here, but I don't know if we'll get there. Let's do this. Let's just talk about what these things mean. So we're going to estimate it, okay? Do you understand how to estimate? You can do that, right? Is the estimate in part A an over or under estimate? So let's figure that out. So it says, on a recent road trip, Mr. Ackerman decided to track his gas mileage during the trip. The efficiency of his car can be modeled by the differentiable function m of g, that's right there, measured in miles per gallon, just double checking that it's labeled for me, where g is the number of gallons, that's labeled also. Gas he's used on the trip. Selected values are given on the table. It is known that m is decreasing for 2 to 12 gallons. All right? And I want to know, is the estimate, so when we do this with right Riemann sums, I want to know if it's an overestimate or an underestimate. So, without getting myself all confused, it says it's decreasing. I'm just going to use kind of the same decreasing graph every time because we don't have to get fancy. These were what kind of Riemann sums? Right Riemann sums. So I go from the right-hand side, so like these are my two, this is my interval here, from the right-hand side and draw to the left. So is it over or under? Under, that's how you know for sure. So we can say estimate from part A is an underestimate. And then you got to make sure your because is for the right reason. Because, all right, now what was the name of the function? This was m of g. It's because whatever this function is, because m of g is decreasing. Now, I do want to talk about C. It's the bonus that we're going to do together. We know that if we integrate this, this is going to be the amount. So when we estimated this value, this is the miles. Because it's how many miles he got, right? And if I take this, which is the number of miles, and I multiply it by 1/10, what do you think that can mean? So what does 10 have to do with anything up here besides this, right? Because that's not where it's coming from. How many gallons did he use that we're looking at? 10. From 2 to 12, that's a total of 10 gallons, right? Now, your cars now, when you have gone however many gallons, you can figure out how many miles per gallon. That stuff's digital. But, you know, back in the day, the only option you had was when you filled up, you did a little division, right? So if this gives me the number of miles, and there's 10 gallons, look at what's happening here. This is miles times 1/10 gallons, right? So that gives him what? It'll give you miles per gallon, which is what the other stuff did too, right? But it gave me miles per gallon at each little interval. So this is miles per gallon over the whole trip. It's the average miles per gallon. It's the average gas mileage he got, which is what we usually look at when we're looking at gas mileage, okay? So to write that out, what did I write out? Yeah. So we would say this is the average mile per gallon, miles per gallon from T equals, no, not T. It's not T. It's not a time. What is it? Gallons. From G equals 2 to G equals 12 gallons. So we're going to start doing some of this too, where you find the whole thing, and it's all in miles, but then when you multiply it by something on here, you're getting a rate back, but it's giving you an average rate over this interval here. Okay. So now with the trapezoid stuff, do you think you could go back and answer the trapezoid questions? Were there also overestimate and underestimate questions? Yes. Okay. So I'm sorry that I'm such a space cadet sometimes. I will go unsubmit all of that so you can go back and rethink about those questions. They're going to be so easy now, aren't they? Yes. Okay.